Good morning, everyone. I'm Mrs. M. Priza Nirmala, working as an associate professor in the Department of Mathematics, Fatima College. Today, I'm going to share with you the concepts of generating functions in the subject combinatorics. First, let us see the definition of ordinary generating function. Let A0, A1, A2, etc., AR, etc. be the symbolic representation of the sequence of numbers. Then the function of the form f of x is equal to a0 into mu naught of x plus a1 mu1 of x plus a2 mu2 of x plus etc. plus ar mu r of x plus etc. This is called the ordinary generating function of the sequence a0, a1, a2, etc. ar, where mu naught of x, mu1 of x, and so on, or the sequence of functions of x that are used as indicators. For example, using 1 comma cos x comma cos 2x comma etc. cos rx comma etc. as the indicator functions, the ordinary generating function of the sequence 1 comma omega square etc. can be written as f of x is equal to 1 plus omega cos x plus omega square cos 2x plus etc. plus omega power r cos rx plus etc. The indicator functions are usually chosen in such a way that no two distinct sequences will yield the same generating function. For this, we'll give one example using 1 comma 1 plus x comma 1 minus x comma 1 plus x square comma 1 minus x square etc. 1 plus x power r comma 1 minus x power r comma etc. as the indicator functions. The ordinary generating function for the sequence 3, 2, 6, 0, 0 is f of x is equal to the product of these two, 3 into 1 plus 2 into 1 plus x plus 6 into 1 minus x. On simplification, we get the value of this is equal to 11 minus 4x, which is the ordinary generating function for the sequence 3, 2, 6, 0, 0. However, when we consider the another set of two sequences like 1, 3, 7, 0, 0 and 1, 2, 6, 1, 1 will also yield the same ordinary generating function. That is, when we multiply the sequence and the indicator function, this is 1 plus 3 into 1 plus x plus 7 into 1 minus x. This on simplification gives 11 minus 4x. And also when we consider the sequence 1, 2, 6, 1, 1, we get 1 plus 2 into 1 plus x plus 6 into 1 minus x plus 1 plus x square plus 1 minus x square, which on simplification gives 11 minus 4x. So when we see the ordinary generating function for the different set of sequences is same. That is, we are getting 11 minus 4x. We should not get it like that. So hence we conclude that the functions 1, 1 plus x, 1 minus x, 1 plus x square and so on, this should not be used as indicator functions. The most usual and the useful form to represent mu r of x is x power r. Therefore, in the case for the sequence a0, a1, a2, etc., ar and so on, we can represent the ordinary generating function in the simplified form as f of x is equal to a0 plus a1x plus a2x square plus etc. plus ar into x power r plus etc. That means mu r of x is x power r. Like the same thing, mu1 of x is x, mu2 of x is x square and so on. Now next we are moving on to the heading generating functions for combinations. First let us see the definition of an enumerator. A generating function that gives the number of combinations or permutations is called an enumerator. Next, the definition for ordinary enumerator. An ordinary generating function that gives the number of combinations or permutations is called an ordinary enumerator. Enumerator means it gives only the generating function. Ordinary enumerator means it gives an ordinary generating function. Next, we are going to see the few problems based on these combinations. First, prove that this notation can be represented as NC0. So the first subdivision is NC0 plus NC1 plus NC2 plus etc. plus NCR plus etc. plus NCN equal to 2 power n. This is the first subdivision we need to prove, and the second subdivision is NC0 minus NC1 plus NC2 etc. minus 1 the whole power r NCR plus etc. plus minus 1 the whole power n NCN equal to 0. So now, coming to the solution of this, we need to consider the identity 1 plus x the whole power n. The expansion of 1 plus x the whole power n is c of n comma 0, which can be in the next step denoted as nc0 plus nc1 into x plus nc2 into x square plus etc. plus ncr into x power r plus etc. plus ncn into x power n. So in this identity, if we substitute instead of x as 1, we'll get the first identity. So when we substitute x as 1, we will get nc0 plus nc1 plus nc2 plus etc. plus ncn equal to 1 plus 1. The value of x is 1. Therefore, 1 plus 1 the whole power n is 2 power n. Hence, we got the first identity. Now, coming to prove the second identity, we need to substitute x is equal to minus 1 in the same identity. So, we will get alternate plus and minus signs with the right hand side value to be is equal to 1 minus 1, because the value of x is minus 1. 1 minus 1 is equal to 0. So, gathering the positive terms on one side and the negative terms on the another side, this identity can be written as NC0 plus NC2 plus NC4 plus etc. equal to NC1 plus NC3 plus NC5 and so on. So we can conclude that the number of ways of selecting an even number of objects is equal to the number of ways of selecting an odd number of objects from n distinct objects. Now coming to the next problem, prove the identity NC1 plus 2 into NC2 plus 3 into NC3 plus etc. plus n into NCN equal to n into 2 power n minus 1. Coming to the solution, we need to consider the same identity 1 plus x the whole power n. By differentiating both sides of this identity, we'll get the value, and by substituting x is equal to 1, we'll get our problem. By substituting x is equal to 1, we'll get our identity. Now, this is a problem of the different type. What is the coefficient of the term x power 23 in 1 plus x power 5 plus x power 9, the whole power 100? So we have expanded, we can very familiarly expand the whole square, whole cube and somewhat to whole power 4. But here we are having whole power 100. So using this generating function, we can easily solve this problem. First, we need to find out x power 23 can be made up in how many ways using the factors x power 5 and x power 9. Now, x power 5 into x power 9 into x power 9 is the only way to make up the term x power 23 in this expansion. We don't have any other term, we don't have any other way to make up this term x power 23. Therefore, when we find out the factors of x power 23, it is x power 5 into x power 9 into x power 9. This is the only way where we can make up this term. So there are two terms, x power 9 is repeating 2 times. Therefore, there are C of 100 comma 2 ways to choose the two factors x power 9. And then there is only one term x power 5. So remaining out of 100, we have selected already 2. Therefore, remaining will be only 98. Therefore, C of 98 comma 1 ways to choose the factor x power 5. Therefore, according to the rule of product, the coefficient of x power 23 is C of 100 comma 2 into C of 98 comma 1, which we will get the answer as, when after simplification, we will get the answer as 4,85,100. Like the same thing, for the same problem, we can find out the coefficients of x power 32 and x power 24. Thank you.